All right, we left our discussion when we had our last face-to-face lecture with calculations of absolute entropies. And this is essentially the last thing in your notes is 21.17 from your book. So either please look at your notes and see that we have this big formula for calculation of S of t, or reference 21.17. This S of t calculation looks like an integral from 0 to t fusion using, all right, Cp for a solid as a function of temperature over T dt. This came from a partial derivative identity. This was the first step. I'm going to put plus dot 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 here because whether you're looking at your notes or you're looking at equation 21.17, we see there's a lot of different things to do. There's delta h's over t's, there's other integrals to do, all right? We went over the basics of that, but there are some details that we have to talk about to execute this math correctly, okay? Just as a quick little review, remember this is an absolute S of t. It was a delta t on this side, but S of t minus S of 0, right, gives us an S of t because we use the third law of thermodynamics, which tells us that S at 0 Kelvin is equal to 0. At 0 Kelvin, we have complete order. We have a disorder of 0, and so we actually get to calculate directly an S of t instead of a delta S at a certain temperature. And that low temperature region, that's actually one of the details we need to discuss. Because as we approach 0 Kelvin, what we end up with is situations where experiments are tough to do, and perhaps more importantly, all the classical ideas that we're using to calculate S of t, right? All the classical functions that we might be using to fit what the heat capacity does as a function of temperature, they stop working. Close to 0 Kelvin, quantum mechanical effects become important. So there's a certain temperature, T low, that we designate for each species, where the classical mechanics and our classical fitting procedures stop working, and where below which, from 0 to T low, quantum mechanical effects become relevant. So what we do is we take this integral and we break it into two parts. We break it not as a whole integral from 0 to T fusion, but as an integral from T low to T fusion, using this same idea, but then also a separate integral from 0 to T low, using a new model that accounts for those quantum mechanical effects, right? The person who did a lot of work associated with this, right, was a guy named Debye, all right, Debye. And he essentially said, okay, I'm going to build this model. It's going to have a fitting parameter in it, but it's also going to mimic experimentally what they saw happen to Cp as a function of t as you did get close to 0, right? And what Debye noticed was that the Cp as a function of t looks like a proportionality constant that I'm just going to call alpha here, and we're going to fill in the details later. It looks like a proportionality constant and then t to the third, right? T cubed. So this is Debye's famous T cubed law. So this is for the areas where we get down into this low temperature. This is how we will deal with heat capacities in that region. So again, one more time, it's not from 0 to T fusion because the same Cp can't be used to describe both the quantum and classical regions. We go from T low to T fusion using our classical Cp, but from 0 to T low, we're going to use a function that looks like this T cubed function, okay? So let's focus on there, and let's write in what alpha actually is. So let's just look at that extra part that we have to add. So what is that entropy up until that low temperature that we would have to calculate to put into our formula? Well, as I just got done saying, it looks like we go from 0, now not all the way up to T fusion or the melting point. We go from 0 to T low, right? 0 to T low. Debye's function for Cp, right, and you'll see this in your book, looks like 12 pi to the fourth over 5 r T over theta d cubed. That's Debye's fitting function. That is Cp for Debye, and that picks up your quantum mechanical effects. Inside this integral, we know that Cp is still divided by t, and we still have to do an integral dt. But this is essentially what we enact in this region from 0 to this T low. Now this T low is going to be different for every sort of material that we look at. And it's something that we have to determine, but in this region, we're going to use this same function, all right? This right here is the only thing that's unfamiliar, this theta d. 12, pi, 5, r, those are familiar. You're going to use your energy r here, just like we normally would. This theta sub d, though, all right, theta sub d, this is what we call the Debye temperature. And it is a fitting parameter. So all that work that you did in lab to fit, right, functions to certain data, certain sets of data, that's all that this is. So for every substance, you're going to have a different Debye temperature. Now there is theory behind how you can get a Debye temperature based off of approximations and using quantum theory, but for now I want you to kind of see it as a fit parameter. So every different substance is going to have a different T low, and every different substance is going to have a different Debye temperature. Okay, so when do you have to use this? Whenever you're given theta d in the problem, and you'll see that in your notes. Or sorry, you'll see that in your homework problems that I assign. So whenever you see theta d, this is what you're going to enact for that region from 0 to T low. But remember, there's that plus ... there. This isn't the only thing that you do. This just accounts for that beginning contribution from 0 to T low. It accounts for those quantum mechanical effects. All right. Sometimes you're asked to account for this, though, and you're not given a Debye temperature. So what do you do in those instances? And you'll see a problem like that as well for your homework. In those instances, you're still going to break it up, but experiments stop at T low. And in those situations, what you're going to do is you're going to find CP for your solid that you're given. And as a good approximation, you evaluate that CP at T low. Notice I'm not doing an integral anymore. I'm literally putting T low, whatever that number is, into CP for the solid. If you take that and divide by 3, then that's a good approximation for S at T low. So this is a lot easier than doing that integral. So when are you allowed to do this? When you're not given theta d. If you're given theta d, you do the integration that I just shown. If theta d is missing from the problem and you still have to account for that quantum mechanical region from 0 to T low, this is the approximation you're going to use instead. Right. In our S of t calculation, there's one other thing that we have to talk about. So we just got done talking about information near 0 Kelvin, right? But there's also information way on the end here, right? From our gas contributions. So the final integral that you'll see written down for that calculation, looks like this. The final integral has CP for your gas. Let me redraw that. CP for your gas over T, dt inside an integral. All right. So this is pretty straightforward. There's nothing we have to worry about it not being able to do experiments, etc. So what do we have to reference here? Well, we've actually been seeing CPs for gases all semester. And so what people like to do here, right, is they like to assume that you have an ideal gas. Now, it won't happen in every problem, but if you assume that you have an ideal gas, right, this integral becomes a lot more straightforward and easy to accomplish. If you assume that you have an ideal gas, then we know for something like a monatomic ideal gas, CP is not a function of temperature. It becomes a constant. So that's real easy then to just kind of pull it out and analyze it and go from there. We know that if it's a diatomic gas, CP has a different value. I think it's 7/2 R, all right? But notice that either way, if that becomes a constant, it's nice from an integration perspective. So what you'll see in these problems is the gas is real, so no gas is truly ideal over this range. What you'll see is, oh, well, if I'm going to make this integral nice and easy to account for just ideal behavior, you'll have to add non-ideal gas corrections to your calculation, non-ideal gas corrections. And the nice thing about these is, well, okay, so experimentally, these would be things that we would actually have to calculate. We'd have to calculate the realness, and we'd either incorporate that in the CP of T, or we would do some extra experiments to see deviations from ideality, and then add that to S of T. The nice thing about the problems is that when you need these, they're there. They're given to you. And all you do is add them to the sum that you're making to accumulate a complete S of T, right? So non-ideal gas corrections, if you're making an ideal gas assumption, are necessary to get a correct S of T. So problems involving calculating S of T are pretty long. You have to stay organized, you have to show your work clearly, and you'll be doing some of those for homework. The last topic we have to talk about, involving entropy just directly as a subject by itself, is encapsulated with this idea called Trouton's rule. And Trouton's rule is a rule that's broken just like most rules in science, but it's also a good rule of thumb to know. And what Trouton's rule says is, when I'm talking about vaporization and I calculate delta SVAP, it's really like an experimental observation. What he found is if he looked at a bunch of different delta SVAPs for a lot of different species, a common number kept on popping up. 88 joules per mole Kelvin. All right. So for a wide range of different molecules, you always get the same delta SVAP. Now this kind of makes sense. If you think about vaporization, you're going from a liquid to a gas. And so you really are accumulating a lot of disorder. All right, it's a pretty big number. So most liquids, right, have a certain order, right, based off of their molecular interactions. Gases we see as almost completely disordered or having a ton of disorder where the interactions are either weak or if we have an ideal gas, they're non-existent. So it kind of makes sense that you get the same change in disorder because most liquids have a certain amount of order and it's broken down to get to that gaseous disordered state, okay? So Trouton's rule works for situations where these liquid interactions are fairly weak. So when you have van der Waals interactions, induced interactions, weak permanent to permanent interactions, permanent dipole interactions, you get about the same value for this all the time or every time. This does not work if you have hydrogen bonding situations like water or if you have strong permanent-to-perm interactions. Strong permanent dipole interactions. For these cases, it wouldn't work. But because it works for most other situations, it's really good to know and to have in your back pocket, all right? It is an approximation, but again, it's a pretty good approximation for most systems that don't involve hydrogen bonds or strong perm-to-perm interactions. This is also useful if you think back to another relationship that we studied before break, and that is how the enthalpy of vaporization relates to the entropy of vaporization. And we know that this is a relationship that is valid, all right? So wait a second, if this delta SVAP is mostly 88 joules per mole Kelvin for most systems, and TVAP is the boiling point, and that's something I can measure pretty readily, I can combine these ideas, and what I can do is get an expression that's a really good approximation for situations where Trouton's rule is valid, a really good approximation for delta HVAP. And that approximation looks like 88 joules per mole Kelvin times your boiling point. So if I can measure a boiling point, all I have to do to get a delta HVAP is multiply it by 88 joules per mole Kelvin, and I'm set for that calculation. This again would be a molar quantity, right? When again is this not valid? It's not valid when you have those strong interactions, but for things like benzene, methane, things that have weak interactions, this is a really good approximation. You're actually going to explore these ideas in your homework as well. So this ends where we're going to discuss entropy directly. Entropy becomes a variable that we discuss as influencing other thermodynamic functions as we move forward. So please try to digest this video, write notes, come up with questions, contact me, and the next video will deal with Gibbs energy and Helmholtz energy.